Welcome to the 26th lecture video for Physics 4C. In this second lecture this week on atomic physics, I have a treat for you, treating a quintessential quantum mechanical system with mostly the amount of mathematics you have covered in lower division so far. We start with a conceptual introduction to the quantum mechanical spin, for which there is no classical analog. And this actually benefits us because that means we have no misaligned classical intuitions to weigh us down as we jump headlong into looking at different features of quantum mechanical spin. As the recorded videos here were part of a worksheet lab activity, in the second segment I read through the introductory section of the lab manual, mainly to make sure to review the matrix algebra that you would have seen in your pre-calculus class. In the remainder of this lecture set, we look at the quantum mechanical states and operators that we previously had to gloss over. We look at the spin states aligned along x-axis, represented in the basis of z-axis spin state. We look at the angular momentum magnitude operator, and we look at the mathematical details of adding two spin 1/2 systems, capped off with a look at the Clebsch-Gordan coefficients table. Now, to be clear, this fun lecture covers materials that are strictly optional, as detailed coverage of spin angular momentum and matrix mechanics is not part of a standard lower division modern physics curriculum. And I do think this material is beneficial for future physics and chemistry major students. Maybe not so much for mechanical or civil engineering students, maybe. So I do highly recommend that you try following the material in this lecture. So let me just give you some context so that what we are doing now for the rest of the lab is not just abstract algebra. Well, it won't. The abstract mathematics. So the physical system I want you to think about is electron. Now you might think we've already been talking about electron. We have not been talking about this particular aspect of electron. So just so that these different contexts are clear, what you have seen, where you have seen the quantum mechanical aspect of electron is in electron in a hydrogen atom. So you have proton here. We can say, all right, it's heavy enough. It's not moving. It's a passive actor. It's not doing anything. And with the description of electron, we started out with somewhat classical description. Maybe it's going in an orbit around it. And then later, with the whole stability of a hydrogen atom and whatnot, we developed it more, and we introduced the de Broglie hypothesis that this behaves like a wave. And one way to explain the stability of a hydrogen atom is that so as it's orbiting, the wavelength of the electron has to be such that if it's a circular standing wave. Like that sounds familiar from when we covered the Bohr model, right? So let me just draw a version of it. So something that looks like this maybe, and if you draw it correctly, then it completes so that it's a circular standing wave. So that's the hypothesis that Bohr made, that angular momentum comes in quantized quantities of h bar. So angular momentum is n times h bar. That's Bohr's hypothesis. As we covered last time, it's not completely correct, but it's starting from correct intuition. And an aspect of this does carry over to the correct, fully quantum mechanical treatment. So I don't want to entirely step away from that. So that's the electron angular momentum we have been talking about so far. And it's different from the kind of angular momentum we are going to talk about now. To draw that distinction in quantum mechanics, we call them by two different names. We call this kind of angular momentum, well, the same thing we've been calling orbital angular momentum.
because it's angular momentum having to do with orbit. And the kind of angular momentum we are going to, that's described by the matrix mechanics that we will work with today is we call that spin angular momentum. And I think the best way to highlight the newness of this idea is to first highlight how spin angular momentum is not a new thing in classical mechanics. So, I mean, you could have talked about spin angular momentum and orbital angular momentum, as in, I don't know what to orbital, let me use this. So if I have this, and I have this little ball, for angular momentum of this ball, I could have talked about its orbital angular momentum as it's going around in orbit. Or I could have talked about its spin angular momentum as it's spinning about its own axis, right? That's where the language is borrowed from. But in classical mechanics, there's no fundamental difference between orbital and spin angular momentum. In classical mechanics, they are both described by the same general relationship, because in classical mechanics, they are both described by angular momentum is equal to r cross p, right? With the orbital angular momentum, what we call orbital angular momentum in classical mechanics, what you're doing is, all right, this thing, it's small enough compared to its lever arm. I can say it's more or less a point mass. So it's point mass orbiting at this, so it's just mvr. Now, if it's a spin, then you have to imagine taking this, breaking a little tiny, this is bigger. You have to imagine taking this, breaking it into tiny little pieces, but each portion of the mass element, you still do apply this. And you integrate it over the entire body, you get the spin angular momentum that way. So in classical mechanics, they are both described by the same basic description. That's what I mean by spin angular momentum is not a new thing in classical mechanics, just a different name for a particular arrangement. So in quantum mechanics, orbital angular momentum, it's not all that new. That's why we could describe it sort of semi-classically. And in fact, when you do a rigorous treatment of orbital angular momentum, the way people do it is, well, you take the classical relationships and you simply turn this into operators. It becomes very much more complicated mathematical thing because now you're dealing with the derivatives and gradients and whatnot. I can actually describe it to three-dimensional. I've given up doing that without prior preparation. Anyways, so it becomes mathematically complicated, but the roadmap is there. It's not something new. That's why I want to tell you that spin angular momentum is a completely new concept in quantum mechanics. Now, to kind of oversimplify it, you might say spin angular momentum is, well, think of electron like a ball. Here's my electron. Think of it like a ball. And it could be spinning, like the way we talk about it in classical mechanics. And if it's spinning like, so if it's spinning in this direction, something like that, look at from top, counterclockwise, then you would say, then it's a spin angular momentum points up. This is the direction of its spin angular momentum. You could say that, and this is sort of like it's a fairy tale. There is a kernel of truth in there, like with many fairy tales, be nice to other people or whatever, but much of it is made up for pedagogical purposes. For one, describing electron like a sphere, that's a completely unphysical description of electron. Electron, as far as we know, is a point particle. It has no size. We have not discovered the structure to electron. We don't know a size of electron. So it's a pointless thing. Like if it's at a single point, how can it be spinning? Like a point doesn't spin. The second thing is this. So if a quantum mechanical spin could somehow be reduced down to orbital angular momentum of some kind, the way it works out in classical mechanics, spin angular momentum would obey a similar rule as what the orbital angular momentum does. And the very first thing you see is that it doesn't, because we are going to be talking about the spin half system. With electron spin, this is the first thing you need to know about its property. We talked about the quantum numbers on Tuesday, right? There's the principal quantum number, orbital angular momentum quantum number, and the magnetic quantum number. So looking at orbital angular quantum number and magnetic quantum number, orbital angular quantum number went 0, 1, 2, and so on. And there was maximum kept by n minus 1. And the magnetic quantum number, it went from minus L plus 1, and so on, all the way to plus L, right? So there are similar set of quantum numbers you can assign to electron that's associated with spin angular momentum. And this is what I'll tell you. Spin angular momentum quantum number is just 1/2. That's for the electron. If you have a different particle, they may have different spin angular momentum magnitude. So if we want to stick with this fairy tale analogy of how electron spin is like this particle, this thing, spinning around some axis, we could say, well, this whole spinning thing, it never slows down. Because no matter what you do to it, it'll always have this spin angular momentum magnitude. It'll never go down to 0. It'll never go up to any other value. The only thing that could change with the electron is what direction that spin points in. And that direction is described by similar magnetic quantum number, m sub s, so that we don't confuse that with this m. And it actually follows the same rule as this does. It starts from minus s, so I guess minus 1/2, and it increases by 1 until it reaches plus s. So minus 1/2 plus 1 is what? Plus 1/2, okay. Oh, I'm already there, so I guess I'm done. So you have two values. So because there's only two values, sometimes we call this a spin up and spin down. Okay. Yeah. So let me point out what makes this so incompatible with the description that we are using for orbital angular momentum. So this description here, it's based on this mental image of something completing a standing wave, right? Look at this thing that has a half integer spin. It doesn't travel in a standing wave. Unless you somehow, for the spin, you give it, when it comes around the once, you decide, that's not enough, go around the one more time. Then it's, why only twice? Why not 3 times? So what it is this is a completely new quantity. Spin, quantum mechanical spin has no classical analog. It's a purely quantum mechanical idea. That's really the best place to start. And you can ground it in one thing, that it is still angular momentum. So depending on the kind of interactions you have, you can have an interaction that conserves the total angular momentum, but where spin angular momentum transfers to the orbital angular momentum by changing this by 1. So it is still angular momentum, but how it's described, there's no analogy in classical mechanics. So that's the context where matrix mechanics is made for. And instead of me lecturing for another 30 minutes, you have the note in front of you. Let me have you read it for however long you need to read through it carefully. I'm going to write down a set of warm-up questions, warm-up calculations. When you feel you're ready, just go through it on your own with your group. And I don't know, let's try calling some people to write down answers when it looks like a lot of people are getting done. Good? Questions? Comments? No? All right. Good. I'll write down the questions and then start walking around.
So you just watched through an introduction to a worksheet lab activity that was done in an in-person class. In that arrangement, students had time to read through the lab manual on their own and work in groups with their classmates. In this online video setting, as a way to fill in the gaps that you have in not having that interactive environment and also not having the printout of the lab manual. Let me display this Worksheet Lab 9 Matrix Mechanics Manual and just read through it. I encourage you to read through the displayed lab manual on your own. I'll start by reading the background material. Background material. We spent a good part of our semester on quantum mechanics, starting with descriptions of early experiments and semi-classical models, which serve to introduce quantum assumptions. The main limitation of semi-classical models, such as the Bohr model, is that they are fundamentally wrong. They start out with the assumption that classical physics is mostly right, carrying out most of the analysis using classical mechanics, and only at a key point asserting a quantum mechanical assumption, such as energy quantization, the de Broglie wavelength, or angular momentum quantization. At some point, you need fully quantum mechanical approaches to obtain a fundamentally correct description of a physical system. One example of this you have seen this semester is the Schrödinger equation, shown on screen here. Let me try to read out the English version of the equation. Minus h bar squared over 2m, double partial derivative with respect to x of capital psi of x and time, plus v of x times capital psi of x and time is equal to I times h bar, single partial derivative with respect to time of capital psi of x and time. You have seen this applied to simple systems such as a particle in an infinite square well, quote unquote, particle in a box, to obtain wave function solutions to the system, which can be used to calculate many physical properties of the system. However, fully quantum mechanical approaches have their own limitations in application. Math. In anything but the simplest possible physical system, particle in a box being just such an example, it becomes necessary to use highly sophisticated mathematical methods. Methods that are frankly out of reach at lower division physics. This limits the number of situations where we can utilize the fully quantum mechanical approaches. Even for the fundamentally important systems as quantum harmonic oscillators, instead of solving the differential equations, we are limited to describing the solutions, either analytical solutions given in the textbook or numerical solutions computed by computer software. This is where matrix mechanics comes in. Matrix mechanics can be thought of as operator-oriented formulation of quantum mechanics. A note, we will only cover 2 formulations of quantum mechanics in this class, but somebody counted 9 different formulations of quantum mechanics. And for those interested, this is the link to the article that counts 9 different formulations of quantum mechanics. It's published in American Journal of Physics, Volume 70, Issue 3, in March 2002 issue. 9 formulations of quantum mechanics. The first author is Daniel F. Steyer. Back to our reading. Somebody counted 9 different formulations of quantum mechanics commonly in use. You have seen some glimpse of operator-oriented approach to quantum mechanics when we introduced the momentum operator, p hat equal to h bar over I, partial derivative with respect to x, and the energy operator, E hat equal to I h bar times partial derivative with respect to time, so that we can express the Schrödinger equation as following, which says that kinetic energy plus potential energy is the energy. The Schrödinger equation is shown on screen. Let me try to read it out. the momentum operator squared over 2m acting on psi of x and time plus the v of x operator acting on psi of x and time is equal to the energy operator acting on psi of x and time. Matrix mechanics offers a particularly elegant and simple description of physical systems. For physical systems that can be described completely by a finite number of states. So unfortunately, this approach does not turn out to be simple for harmonic oscillators or the hydrogen atom. One physical system that does have a finite number of states and can be described and analyzed simply and elegantly using matrix mechanics is the system of quantum mechanical spin. So, we will use this as a case study to teach you a little bit about matrix mechanics and quantum mechanical calculations represented in this formalism. One important note, none of this is in standard physics 4C curriculum. So you won't see anything in your homework exercises or exam questions that requires you to know matrix mechanics. Think instead of this as a series of fun exercises that might help you further develop your quantum mechanical intuition. Quantum mechanics is notoriously difficult to understand at an intuitive level. Many classical images and intuitions we have hurt more often than they help. Shut up and calculate is a mantra in modern physics for a reason. It is often easier to perform rigorous calculations in a formalism of quantum mechanics than it is to assign meaning to every aspect of the calculation. This is covered under the heading of interpretations of quantum mechanics. While nearly everything we do in physics 4C includes some conceptual pictures, making it possible for some aspect of classical image or intuition to misinform and mislead your thinking, matrix mechanics approach to spin systems is the first example where you can simply perform the rigorous quantum mechanical calculations without reliance of classical images. Matrix algebra. Physics 4C co-requires Math 3E, linear algebra, so you should be familiar with the matrix algebra. But we will recap some key points here. We won't use everything you learn in Math 3E, but on the flip side, whereas you dealt with real linear vector spaces in Math 3E, our matrices are going to allow for complex elements, which means we are dealing with a complex linear vector space. So watch out for any definitions or results that are applicable only to real linear vector spaces and not complex vector spaces. In these calculations, you will only see three kinds of matrices. The first is a column vector that might look like, on the screen is an example of a column vector. Psi is equal to vertically oriented elements of A and B enclosed by round parentheses. This can be used to describe a system with only two distinct states. If we have more states, we will need to use higher dimensional vectors, 3 by 1 column vector, for example, to describe a three-state system. The second is a row vector. On the screen is shown the example of row vector, which I'll read out loud. Psi transpose is equal to, and the two elements A and B arranged horizontally, again enclosed by round parentheses. This can be obtained by taking the transpose of the column vector. You have seen wave function psi of x and complex conjugate of wave function psi complex conjugate of x, which can be used, for example, to calculate the probability density. P of x is equal to complex conjugate of psi times psi, that gives psi modulo squared of x. The matrix mechanics version of that is psi transpose complex conjugate times psi. Note that in the matrix version, the order of multiplication is important. Finally, the operators in matrix mechanics are represented by square matrices. For example, an operator that could act on the state psi above would look like, and on the screen is an example of an operator H, and that looks like H is equal to a square arrangement of H11 and to the right H12, that's row 1 of H matrix, and then H21, and to the right H22, that's the row 2 of the H matrix, again enclosed by round parentheses. Now, for the algebraic operations that you might do, following are two operations that follow simple, straightforward rules that hopefully don't need much explaining. Addition, you simply add the matrices element by element. For example, if you have two 2 by 2 square matrices A and B, then on the screen is shown the operation of A plus B. It shows the two square matrices A and B. You add them by element, that results in a single 2 by 2 square matrix that has as its elements, starting from the left to top, going to right, and row by row, you have A11 plus B11. Next element in row 1 is A12 plus B12. And the first element in row 2 is A21 plus B21. And the second element in row 2 is A22 plus B22, enclosed by round parentheses. The second operation is scalar multiplication. When you are multiplying by a simple number, scalar, you simply multiply the number to every element of the matrix. For example, multiplying A above by scalar C, you get C times A is equal to C multiplied to operator A gives you the following four elements of this matrix. Row 1, element 1, C times A11. The second element in row 1 is C times A12. And the first element of row 2 is C times A21. And the second element of row 2 is C times A22, again enclosed by round parentheses. As in usual algebra, subtraction and scalar division follow the same rule. That is, subtraction is just addition of A and minus B. Scalar division is multiplication by 1 over C. It's the matrix multiplication that requires some reminder explanation. When you multiply two matrices together, you do not multiply them element by element. You could do such operation. It's not called matrix multiplication. Instead, you take a row from the first matrix and a column from the second matrix. You multiply these two element by element. The row vector and the column vector must be the same length. And you take the sum of these numbers. This is an element of the product matrix. The number of the row that you took and the number of the column that you took become the row and column number of the element. This rule looks as following in the summation notation. Subscript denotes the row and column number for the element in order. So the A times B sub ij, meaning row I, column j of the product A times B, is equal to summation of k from 1 to L of A sub ik times B sub kj, where L is the number of columns in A, must be the same as number of rows in B. So, if you have two 2 by 2 square matrices A and B, this is what their product looks like. On the screen are shown the product A times B, and the product of the two matrices result in the following element. Row 1, column 1, A11 times B11 plus A12 times B21. Row 1, column 2, A11 times B12 plus A12 times B22. Row 2, column 1, A21 times B11 plus A22 times B21, and finally row 2 column 2, A21 times B12 plus A22 times B22. You work out each element of the product matrix one at a time. I visualize going quote-unquote across matrix A and quote-unquote down matrix B as I do it, but different mental calculation techniques might work for different people. We can use this matrix product to take the inner product. For example, with the two-state vector you saw before, psi, we can compute psi modulo squared being defined as psi transpose complex conjugate times psi. So this looks like a product of a row vector, A complex conjugate and B complex conjugate as the two elements, being multiplied to the column vector of A and B. The matrix product results in A complex conjugate times A plus B complex conjugate times B, just one element. And this is equal to A modulo squared plus B modulo squared. Once you get into upper division quantum mechanics, you will learn about the bracket notation, which expresses these operations elegantly. Spin 1/2 system. The spin 1/2 system gives a perfect testing ground for exercising your muscles with the formalism of matrix mechanics. It is a commonly occurring, real physical system. An electron is a spin 1/2 system, as are many other subatomic particles. And it contains the fewest number of possible states, excepting those that have only a single state, which does not allow for any interesting structures. A few weeks ago, you have seen Bohr's semi-classical model of the hydrogen, with the Bohr's quantum mechanical assumption being introduced as L equal to nh bar, his assumption that orbital angular momentum is quantized. It turns out he was absolutely correct on this aspect of the model. In addition, this assumption also holds for the spin angular momentum of the electron. The electron has an intrinsic angular momentum that we call spin. This name is given in analogy to the classical spin. Imagine the angular momentum of a spinning top. But it really has no classical counterpart. For one, the electron doesn't have some constituent parts that could move around their mutual center of mass. When the electron spin is measured, or more precisely, when the component of electron spin along z-axis is measured, it is found that it comes in two values, S sub z equal to plus h bar over 2, and S sub z equal to minus h bar over 2. These half integer values do not occur with the orbital angular momentum, but what is still consistent with Bohr's quantization rule is that the difference between these spin values is still h bar. Delta S sub z is equal to plus h bar over 2 minus h bar over 2 is equal to h bar. Because quantum mechanical spin is so foreign to classical mechanics, for better or worse, when we want to work out the mechanics for the spin, we cannot use the approach previously used, where we use the de Broglie relation to transfer our intuition about classical mechanics, for example, kinetic energy being equal to momentum squared over 2m, and so on. Transfer intuition to quantum mechanics and apply quantum mechanical rules. This time, there is no classical intuition we can use, since there's no classical analog we can compare to. Instead, we will get to build our description from scratch using matrix mechanics, first by describing the quantum states and coming up with operators we can use to measure properties of these states. Measurement and measured values of physical observables in quantum mechanics is specified by use of operators, Hermitian operators, by which we mean square matrices, which satisfy the property operator A is equal to A transpose complex conjugate. These operators represent physical observables, and the physical properties of a state psi are measured by the operator acting on the state vector. In matrix representation, an operator acting on a state vector is multiplying the state vector with the operator. Watch the order of multiplication. For a column vector, the operator has to multiply from left. And for a row vector, the operator has to multiply from right for the matrix multiplication to make sense. Given a physical observable A, there are special set of vectors psi which satisfy the following relationship. The operator A multiplied to psi is equal to lowercase a multiplied to psi, where lowercase a is a scalar. That is, when you multiply the column vector psi with the square matrix A, you get the same vector psi back, multiplied by a simple scalar. Vectors that satisfy this relationship are called eigenvectors or eigenstates. What this means is, for the physical observable A, these states have a definite value for this property, and A is that value. More generally, a general state vector phi does not satisfy above relationship, but it can be written as a linear combination of eigenvectors. For example, if you have two eigenvectors psi A and psi B, the eigenvector relationship being operator A times psi A is equal to the lowercase a times psi A, and the operator A times psi B being equal to the lowercase b times psi B. The two eigenvectors, and suppose phi can be written as phi is equal to psi A plus psi B or other linear combination. As long as A is not equal to B, you can see that phi does not satisfy above property. Operator A acting on phi is equal to operator A acting on psi A plus operator A acting on psi B, which gives lowercase a times psi A plus lowercase b times psi B, and the last expression cannot be factored out into a form of constant scalar times psi A plus psi B. For these general states without a definite value of measurement by A, you can only talk about measurements in probabilistic terms. For example, when A measures phi above, you have 50% chance of getting A and 50% chance of getting B. Or more practically for land measurement, you can talk about expectation values of measurements. Following is the algebraic procedure for computing expectation value A of observable operator A of a state phi, with the explanation shortly following. The expectation value A in angle bracket is equal to the transpose of phi complex conjugate times the operator A times phi divided by this whole thing, phi transpose complex conjugate times phi. This is how the calculation works out. Let's say you can express phi as a linear combination of eigenstates, psi I. Then phi being equal to summation over index I running from 1 to n, summation of products, c sub I times psi I, where c sub I is a scalar and n is the number of eigenstates, which spans the space to be technical. If each psi sub I has eigenvalue lambda sub I, we can express the multiplication A times phi as following. A times phi is equal to A times the summation of index I running from 1 to n, and the terms being added are c sub I times psi sub I. And this is equal to, utilizing the fact that we know the result of A acting on each individual psi I, it's equal to the summation over index I from 1 to n of the following product, lambda sub I times c sub I times psi I. Now the numerator for expectation value A is technically a messy double summation. But because of the orthonormal property of psi I from being eigenvectors, all the cross terms vanish to 0. That is, psi of j transpose complex conjugate times psi of I is equal to 0 unless I is equal to j. And psi sub I transpose complex conjugate times psi sub I is equal to 1 from the orthonormal property. So we get this simple result for the numerator. Phi transpose complex conjugate times operator A times phi is equal to sum over index j running from 1 to n, c sub j complex conjugate times psi transpose sub j complex conjugate, this whole summation times another summation running with the index I from 1 to n, lambda sub I times c sub I times psi sub I. And when these two summations are multiplied together and we use the above orthonormal property, the result is summation over index I from 1 to n, with each term being lambda sub I times modulo squared of c sub I. I hope this reminds you of the general expectation value formula, or also known as expected value in statistics, where expectation value is the sum of products of values of outcome and probability of the outcome occurring. The only wrinkle here is that c sub I modulo squared may not add up to 1, in which case you can interpret it as probability of each outcome. This is why we divide by phi transpose complex conjugate times phi, being equal to summation of index I running from 1 to n of c sub I modulo squared. In another description, this normalizes the potentially unnormalized state phi. That's the background material. Now, part A, spin operators. With the background material out of the way, I think you are now ready to build a mechanical description of a spin one-half system, starting with a guess at the operators. We use the column vectors to represent the two spin states for the spin half system, one for s sub z equal to plus h bar over 2, quote-unquote spin up, and another for s sub z equal to minus h bar over 2, quote-unquote spin down. We will use following simple forms. Psi spin up is equal to column vector 1, 0, and psi spin down is equal to column vector 0, 1. These forms have some nice properties. Inner product of two distinct states is 0. Psi spin up transpose complex conjugate times psi spin down is equal to 0. And inner product of a state with itself is 1. Psi spin up transpose complex conjugate times psi spin up is equal to 1, for example. This property is called orthonormal, a combination of orthogonal and normalized. And many calculation procedures in matrix mechanics assume you are working with an orthonormal basis. Basis means any other state can be written as a linear combination of these basis vectors. For example, if phi is equal to column vector of A and B, A being row 1, B being row 2, then we can write it as phi is equal to A psi spin up plus B psi spin down. With this, the stage is set for finding the form of the operator S sub z, the operator which measures the projection of the spin along the
So for those people who are getting started early, there's some additional piece of information that I'm giving to you now that's not in the note. So in the note, I gave you this, the operator for measuring the g component of spin angular momentum. Or if you're not there yet, you'll get there. These are the operators that measure the x component and y component of spin angular momentum. Okay? You need to be given these operator forms, otherwise it's not something you can guess. I guess if you look at this, it's something called the Pauli matrices. If you're not look them up, look up Pauli matrices. That's what those are. Well, that's what those are based on. This h bar over 2 is needed there. So, anyways, I just want to explain that these are the questions. Whenever you're done reading, start working on the questions. I'll walk around and answer any questions. Okay, can I take 2 volunteers to do questions 1 and 2? Do I have volunteer from, I don't know, group in the center? Volunteer to do question 1? Okay, function, you volunteer for question 2? Yeah, okay, could you please come up, right? I have pens here, and we'll see if they do it correctly. Thank you. Yeah, thank you, Kian and function. So yeah, that's it. So this is, it's not a difficult calculation, but this is showing the basic idea behind what we are calculating and what it's for. So you have a state which you maybe suspect is a eigenstate, or it's a state with a definite particular value for the thing you are measuring. And if your guess turns out to be correct, then after you apply the operator, by which we mean do the matrix multiplication, you get an end result that you can factor into the original state, and a simple scalar coefficient. And when you have done that, this simple scalar coefficient, this represents your measurement. So the first result, Kian got plus h bar over 2. So that's a spin pointing in the positive z direction, or spin up. And here, function got, after going through the calculation, after factoring out the state, the original spin down state, 0, 1, right, so factor out minus here, this minus h bar over 2, this is the measurement. So that's the basic scheme. That's the basic mathematical formalism. That's what we are calculating means. And in fact, we've been doing this already. We've been doing this with wave mechanics too. So we could have, what we were describing with the momentum operators, we could have done it with the matrices, except it would have been very unusual. You would use rows and columns to indicate some kind of, I don't know, polynomial or something. Then I won't get into that. You will see that in your linear algebra class if you need to. So now, this only works for very special states that are eigenstates of the operator. If you don't have that, then it gets a little bit more complicated. So in the note, it described how to calculate the expectation value that we have been already doing somewhat in wave mechanics. And this is an example of expectation value calculation. What did the people get when you calculate that? You got 0, and that makes intuitive sense to you? That, okay. So when you look at this state, you might say, oh, so it has, or kind of divide it this way. This is the spin up portion of it. This is the spin down portion of it. So maybe intuitively you say it has equal portion of spin up and spin down. So when you take the average, it should average out to 0, right? Yeah, if you did a calculation and it made the intuitive sense to you that way, then great. Anyone have any question on this question? Let's spend a little more time on question 4. It's asking for sorry, I'm hesitating between different terminology. So you could call this a vector, wave function. The one I kind of want you to call it, but we haven't used in this class so far, is a spinor. Spinor is the more specific term for the mathematical object we are dealing with. But let's call it vector. So find the vector which satisfies this particular relationship. So, so this is a simple enough of an operator that we can kind of guess and check. So let me do that. I think many of you derived the result already, probably. But I kind of need When you did that, did you get this as your result? No? I'm not getting all of that. Okay, so it's probably something different. I don't know. I just came up with that one just on the spot. So this wasn't meant to be this. So if it didn't turn out to be that, then great. That we avoided an accident. So for question 4, what we were tasked to do is we had this particular equation. So let's just give it some labels. The spin up in the x direction, which will have components a and b. And these are potentially complex numbers. Maybe not. And what these a and b need to satisfy is this equation. The multiplication by the x spin operator, h bar over 2, 0, 1, 1, 0. That multiplied by this vector is equal to the scalar that we suspect is one of the eigenvalues, or one of the possible measurements by the operator, times, I want the same vector back. So let's simplify some things already. So h bar over 2 cancels out, can get rid of that. And there is a systematic way to do it. The systematic way to do it would be to kind of write out your system of equations. Because what this represents is a system of 2 equations. Because when you write it out, you know, this times this gives you the first row. This times this gives you your second row. So maybe I should do it that way. Wait, so when you do that, yeah, so the result you get is A equals B, right? That's what you need for this to be satisfied. Yeah, so that accident I was afraid of happened. So if A is equal to B, then what your vector has to be is this. So it's instead of AB, it's AA. A vector of this form would satisfy that. Or you could even write it as, A times 1, 1. And I think I'm now realizing what happened. So I was asking you guys if you got the result for this as this. And let me ask you this. If this A and B, if they were like what you had in that vector, 1 over square root of 2, 1 over square root of 2, is this equation still satisfied? It is, right? So what meaning does the value of A have? It has no physical meaning. This A here, this is what we have been calling normalization coefficient. You've heard this mentioned in the wave mechanics context, right? So you also have normalization coefficient in the matrix mechanics. And this here is something kind of you see new in quantum mechanics. The kind of vectors we use in quantum mechanics, these vectors, their magnitudes have no, or their amplitude, their size has no physical meaning. So the reason this was written this way, this is a normalized vector. So when you calculate this, it's automatically already expectation value. If I gave you a vector that's not normalized, like this one, then you would have to divide this by the dot product of the vector with itself so that the end result would be normalized. Good. So what this answer for question 4, what that's revealing is that this state here, what this is X spin-up state. As in, this represents a spin state which is pointing in positive X direction. Then it sort of, does that make intuitive sense? That if you had So if you had a spin up or spin down, and you measure the expectation value, then you would measure spin up or spin down. But if you had a spin, like pointing in the x direction, and you measure the average value of spin up and spin down, then this has on average 0 spin up or spin down. Right? Yeah, so that makes intuitive sense, right? Yeah, so all right, so far so good. And I gave you only one question because we have limited time in lab. But if you want to do more exercises for your own benefit, then what you can do is, well, you could find one that satisfies minus h bar over 2. What would it look like if you're looking to find the spin down, x spin down state? Like, you can do that on your own. Oh, and you can also do it for SY, and you can also do it for SY. Both the spin up and spin down, it's like spin going in this direction and spin going in this direction. So I'll leave that for you. And what you will find that all of those states will be a linear combination of these two. So all those for y direction it'll be complex because of this, but they will all be linear combination of these two. So yeah, I guess that's kind of it. All right. How many people are done with the 5 and 6? How many people are done with the 5? Okay, I guess enough of you are done with the 5. Let me go through 5 because this is the one where there's a kind of there's a mathematical language here that once you learn it, it becomes very elegant and simple way to work it out. But when you don't know it, it's like being in a foreign country and your vocabulary doesn't include whatever words they are using. So let me just write it out in a way that kind of expands out what's hidden in this kind of compact notation. I have done the first step here, but let me do a few more so that it's all kind of spelled out for everyone to see. So we are trying to calculate s squared operator. And the word operator gives, well, once you know the language, it gives you a hint that you are looking for square matrix. Because in the way we are working, our representation of operator is a square matrix. All right? So let me do a few more algebra notations. What this s squared means, as I wrote down there, it means s dot product with s. You know what? Let me just be extra careful and go one more step. This vector s, this is how you can represent it. You can represent it as in the unit vector form. So the x component times x hat. Actually, let me swap the order so that there's no confusion here. X hat times the x component plus y hat times y component plus z hat times z component times dot product with x hat times x component plus y hat times y component plus z hat times z component. Good. I want you to write it out this way because this is a chance to kind of clarify two different kinds of vectors we are using. So these are unit vectors, right? That you already know. Any guesses how these unit vectors relate to these vectors we've been talking about? It's a trick question. The answer is not at all. There are two different kinds of vectors entirely. This is a state vector. That's a physical three-dimensional vector, direction vector. That's why I hesitated on calling this a vector, because when you call it spinor, then you make it clear that this is an entirely different mathematical object from vectors that's like arrows that point in different three-dimensional space. This state vector is it's a linear algebra vector. It's an abstract vector, a linear vector space vector. Yes?
So is that SX operator, does that give you the state or does that give you the direction?
It's an operator. It's something to act on a vector with. But until you act on a vector with that, you don't actually have anything.
But like what does it return? Does it return a state or does it return a...
Yeah, when you multiply a square matrix to a column vector, you get a column vector back, right? So you get a state back. Yeah. Yeah, oh, but yeah, so when you act on, yeah, let's leave it there. Good. And if you wanted to measure this, actually, so here I'm kind of omitting something as a matter of convention. So all this is an operator algebra, and this is more of an upper limiter. It's easy to make a mistake on operator algebra because this whole operator objects, they're different from functions and other things, numbers that you may have been dealing with. The advice I was given when I was taking linear algebra or whatever is that to make sure that you don't make any mistake in the operator algebra, always imagine that you are acting on a state with that operator. Imagine that you are acting on a particular state with that operator. You are acting on a particular state with these operators. So with all this, imagine you are acting on a particular state. And whatever steps you go through, make sure you are not doing anything that's mathematically disallowed. And at the very end, ignore these states, then you will have done correct operator algebra. Yeah. All right, so let's go through the rest. So the reason I'm kind of doing this notation hides a lot of complexity that could potentially be there because the notations and rules of algebra that you've been taught since middle school? No, algebra. My go-to word is kindergarten, and I know that's wrong for algebra. Elementary school, PEMDAS or whatever. Those rules, they apply to graduate level abstract math. They teach you from below because all those rules about distributive law, associative property, they continue to hold with this new mathematical object. So I'm just going to use that. The one thing I'm going to be careful with is when you're dealing with the operators, they are potentially non-commutative. So I'm going to be very careful when I swap the order of any product, just in case whatever I'm dealing with are non-commutative. Okay? So other than that, let me just go through it. So I guess it's kind of easier to just kind of write it out. So I have, all right, let's, okay, I don't want to write out the whole thing. So let me just highlight this, and then I want write out the whole thing. So I have this. When I distribute this product, when I expand out this multiplication, I have this thing multiplying to this, this, right? So potentially, let me write down the first one. I have x hat dot sx times x hat times sx. Okay? And I guess the key thing that's important here is this dot product. So let me just highlight that dot product. Okay? I just mentioned that how these products are potentially non-commutative. So I would be careful about swapping any order. So this is what I would ask. Well, how does this x hat vector interact with this operator? Do they interact with each other at all? They live in completely separate space. What this vector represents and what the operator represents is like two orthogonal things. They don't affect each other. So this is where I'm going to just find, well, I can actually move this past this operator. And I have this dot product. And actually, this dot product was meant to be for three-dimensional space vectors. So I have x dot x. That's 1, right? OK. So I have, so simplifying that, I have sx matrix product with sx. That's it. And when you look at these other two products, x dot y gives you 0. X dot z gives you 0 again. So, and when you go through that for all these three terms, what you end with is what many of you probably used, just intuitively. sy plus sg. So if you did that intuitively, great. In this case, there was no mistake. The reason I wanted to work through this in detail was sometimes with the new notations, if your intuition continues to work, great. But if not, you need to be able to kind of unpack the notation, work it out step by step, and then do it. All right, so let me just do this calculation then. So I need to calculate this which would be, let me just do the coefficient on its own, h bar squared. So when I do this, I get h bar squared over 4 times. So I have to, I guess I should write it out. So 0, 1, 1, 0, multiply to 0, 1, 1, 0. All right, let's work it out and see what I get. H bar over 4. This times this, that's 1, right? Yeah. Yeah, visually, by the way, that's what I do. I imagine going across as I go down. That kind of is a quick visual way to. So this times this is 0, right? 0, 1, 1, 0. This times this, so let me write down that 0. This times this is 0 again, so 0. And this times this is 1. All right. This is an identity matrix multiplied to a scalar. I guess in terms of operators, this is as close to a scalar as you can come. Because a scalar times identity matrix, you can multiply to anything else that has the right dimensions, and you'll just get essentially scalar multiplication. Let's do this. Actually, everyone has done this. Did you get this exact same thing for each one of these? Yes? Not everyone? Raise your hand if you got this thing for this and this. Well, let me go through it. Yeah. All right, so when you do this, all right, so you get this factor twice again, h bar squared over 4 times, let me write this out, 0 minus I 0 times 0 minus I 0. All right, so that's equal to h bar, mix some 4, this times this. Minus I times I, what does that give you? Negative I squared. I is the imaginary number. What is I squared? Negative 1. So negative I squared is 1. Yeah, so it's still 1. Yeah. Okay, so this times, wait. Okay, so this times that is 0 again. So 0. This times this is 0 again. And this times this is, once again, 1. Yeah. So, they end up being the same. And when you do SCG squared, you also end up getting the same thing as this. So the overall result is h bar squared, is equal to 3 h bar squared over 4 times the identity matrix. And this actually agrees with something that you were told on Tuesday. With the quantum numbers on Tuesday, this is what you were told. Let me just write down. So remember the L quantum number, right? L quantum number goes from 0, 1, 2, whatever. And we said this is the angular momentum quantum number. And we said this is related to the magnitude of angular momentum. And that the magnitude of angular momentum is equal to h bar times square root of L times L plus 1. That ring a bell? Yes? Now, let's just imagine that this relationship for angular momentum continue to apply to the spin angular momentum. Then you would say, okay, magnitude, spin squared should be h bar squared times, get rid of the square root, the quantum number s, times s plus 1. So s is 1/2 in our case. Is this s 3 over 4? Is that s times s plus 1? 1/2 times 1/2 plus 1, 3/2. Yeah. Yeah, so that's it. So I mean, this doesn't prove anything, but it shows that the rules that spin angular momentum satisfies is same as the rules that the orbital angular momentum satisfies, and you saw it rigorously. So when we did this, we just gave you the rule. You didn't drive this anywhere. But with the matrix mechanics, you can see rigorously that yes, this is the eigenvalue. This is the actual measurement of the angular momentum magnitude squared. Yeah. Question number 6. So how many, everyone done question number 6? And you kind of guess the answer here from saying that this is an identity matrix. You're just going to get the same state back with this coefficient here, which means this particular state, which is a mixture of a spin up and spin down, it still has this spin angular momentum magnitude. It doesn't have a spin 0. And I was telling some of you that you can draw analogy between this and the polarization of light. If you recall back to when we did optics, this is precisely what I said. You could think of unpolarized light as having half of its intensity in the vertical polarization and half of its intensity in the horizontal polarization. And Gauge objected to that description. And that objection is right. It's wrong, right and wrong. It's wrong in the sense that all I said that you can think of it that way. But the objection is right in that if you had a combination of vertically polarized light and horizontally polarized light, you would not have an unpolarized light. You would have a polarization that's diagonally polarized. And that's what you have here. When you have spin up, combination of spin up and spin down, you don't have zero spin. You don't have unpolarized spin. You simply have a spin that's polarized in a different direction. Good? Yeah, so I'm not going to really get into unpolarized states. Unpolarized states are really complicated to deal with. If we want to look at how people handle unpolarized or polarization or, I guess, incoherent quantum states, the only mathematical formalism that can handle that is something called density matrix formalism. And in fact, this is something that my research group worked a lot with because that's what aim of physics groups do. But that's even above upper division quantum mechanics. So it's only for people who are interested. For the rest of today, what I wanted to do was kind of describe how you would combine actual spin states. So if you're trying to describe mixture of spin up state and spin down state, you simply get another spin half that's pointing in a different direction. Okay, so let's give that up. Let's instead do this. Let's try to say, okay, I have one spin half particle, and instead of trying to put this into spin 0 state, which is not possible, we kind of knew that, right? Because when you look at the quantum numbers, there's only plus h/2 and minus h/2. There's no 0. So instead of trying to put this into spin 0 state, we are going to say, all right, I'm going to add another spin half system. And maybe by adding them together, I can make their total spin 0. Yeah. OK, so this is where I need to lecture a little bit to at least give you some intuitive feel for the mathematical operation we are going to do. It leads into something called the product space. How many here have heard of product space? So, I mean, that's an upper division level math. Actually, you've seen product space, the Cartesian three-dimensional space. That's a product space of one dimension, second dimension, third dimension. That's how you deal with the orthogonal spaces that don't affect each other. But you wouldn't say there's like a code product space until you get to upper division mathematics. So I don't have any material written for that because this note that I wrote up was for high school students. So that's why I need to lecture on this a little bit to give you some sense of intuition and how to handle when you are adding two particles where they are not supposed to affect each other. So this is what I mean that they are not supposed to affect each other. So well, take this as an example. If I took this as a system, and let's say I made a measurement of the z. I made a measurement of the z projection of the first particle. I could say, all right, act on this with the z component for the first particle. So the way I drew it, it's a spin up. So I would expect to get plus h bar over 2 from this spin up. And this state would be left undisturbed, right? That's what you saw when you are doing calculation, right? what do you think should happen to the state number 2? How many say nothing? Yeah, nothing. I'm measuring particle 1. For all I know, they could be miles apart. So the operation I'm doing to particle 1, it ideally shouldn't affect the particle 2. So, all right, so particle 2 should be left undisturbed. So this is the state you should have with. So that's the operation you ought to be able to. Now, imagine you are, instead of measuring G component of particle 1, you are measuring the, I don't know, you are measuring the X component of particle 2. Should anything happen to particle 1? Nothing. So the state of particle 1 should remain as it is. Does it look like something ought to happen to particle? Like, would I remain with the same state at the end? Yeah, this is not in an X component eigenstate, right? It's some mixture of whatever. So the particle 2, in general, it would be something else, like some other state 2. And in fact, since it's not an eigenstate, we are not going to have this nice thing. It's going to be some number that whatever it is. So that's the paradigm that I'm trying to describe, that whatever, but I guess what remains true is that the state 1 didn't change at all. So if you took this, and then if you measured the G component of particle 1 now, then you would get what you are supposed to get. You know, this thing times h bar over 2. That's what you would get. Because whatever you did with the particle 2, it did not affect particle 1. So that's the underlying picture that we are now trying to describe with our math. So this is described with a formal structure called the direct product space. The way you would kind of indicate it is like, so state of particle 1, product, so let's say times, but I want to make sure it's not any kind of product that you know. So let's say circle. And this is not associated with anything else in your mind. So I'm just going to write that. Times the particle state 2. And kind of basic rule is that so this is the state that describes the entire system, the system with the particles 1 and particle 2. And you can do a bunch of different operations here. You can do any of these component operations, x, y, z on particle 1 or x, y, z on particle 2. Or you can do this, the s squared thing that we derived before. You can do s squared for particle 1. You can do s squared for particle 2. Yep. Now, let's think about trying to build a zero angular momentum state. Like, it ought to be possible, right? So it ought to be possible to somehow combine. So this is spin up. This is particle 1. This is particle 2. It ought to be able to somehow combine this spin up and particle 1 with a spin up, for example, with a particle 2 in a particular state, so that they add up to 0. Maybe spin down. Then, like, this combined state ought to represent a spin 0 state. Yes? Okay, so let's try that. So place I'm leading, I'm saying, okay, so for 0 spin, let's try this. For 0 spin, well, I have this spin. Let me use this, symbols, because I'm actually going to use slightly different matrices than these. So let me stick with the symbols. So for particle 1, I use a spin up state. So spin up particle 1 in direct product with spin down particle 2. All right, so if this is what we think is a 0 spin state, how would you measure for a fact that it has 0 spin? What kind of mathematical operation would you do to prove that this particle state has 0 spin?
Apply the S-squared operator.
S-squared operator. All right, let me try that. So if I apply S-squared operator to psi spin up 1x, psi spin down 2. Well, let me do it in a way that is going to be a mistake, but it's a common mistake to make. It's the mistake I made when I was an undergrad, when I was unfamiliar with the notations. The easy mistake to make is, oh, S squared. Well, this is an eigenstate of that, so I get h bar squared 3 over 4, and the same state back. Oops, something went wrong. I wasn't supposed to get this, right? What did I do wrong?
It's not an eigenstate anymore.
No, it's a little bit more complicated than that. So this S squared it's ill-defined. Did I mean S1 squared? Did I mean S2 squared? Either way, whether it was S1 squared or S2 squared, this is actually correct. And of course that's correct because your particles still retain their distinct identity. If you're measuring the angular momentum magnitude of a spin particle 1, then of course that you should measure that. Like that's not a wrong result. It's just not what you thought you were calculating, right? So let me spell this out a little bit more carefully. Let me start by defining a new variable so that we are not making this rookie naive mistakes. Let me define a total angular momentum operator. I'm going to call it J. It's a common symbol. J, total angular momentum operator. And I'm going to put vector symbol on it because angular momentum is a vector. Well, from classical physics, what do you think this ought to be equal to? We are not doing orbital angular momentum. We are just this is a vector operator, which is supposed to be the total sum of 2 other vectors. Just add that, right? It's the sum of S1 plus S2. That's what it's supposed to be, so I'm keeping it that way. Okay? And all right, now I don't really want to deal with the vector operators. I do want J squared. And what J squared is, well, it's a J dotted to itself. Or let me expand it out with this. It's S1 plus S2 dotted to S1 plus S2. So when I'm just writing down the algebra, it doesn't look like I'm doing anything different from what you are used to doing. But this is the reason we spend so much time on doing the other one in more detail. Because what these are they are operators, and there's each symbol represents a more complex mathematical object than what you're used to dealing with so far. So, but let me go through it. The outside look is actually still remains simple. S1 dotted to S1 itself. Well, that's, I guess, going to be S1 squared, right? And S1 dotted to S2. All right, I don't know what that is, so let me just write it out. Plus S1 vector dotted to S2. We'll just leave it there for now. S2 dotted to S1. I also don't know what that means, so let me just write it out. S2 dotted to S1. And S2 dotted to S2. So you get plus S2 squared. All right, at least the 2 of those things I know what to do with. This I know what to do with, this I know what to do with. And these, well, I guess if I expand it out, it's going to be S1x times S2x plus S1y plus times S. It is possible to work through this. So let me just try to work through this. And I can show you that this state, it's an eigenstate of the G operator, That's what this was. But it is not an eigenstate of the total angular momentum magnitude operator. So, so this, yeah, that's what happens when you're improvising. So we just need to work this out. So S1 squared, I think I understand this operator well. So I can leave that alone. This operator, I understand it well enough, so I can leave that alone. The operator that I need to deal with are these. So let me just write it out. S1 squared plus S2 squared plus, and I'm just going to write these two out. It's going to be S1x, S2x, plus S1 y, S2y, plus S1g, S2g, that plus the order swapped, S2x times S1x plus S2y times S1y plus S2g times S1g. Here's a question. So far I've been treating these two as if they don't commute because I wanted to be careful. Do they actually commute? In the sense of if you measured x component of particle 2 first and then the particle 1, or if you swap the order, would that matter? No, right? Because they don't, like this doesn't affect any particle 1 state, and this doesn't affect any particle 2 state. So what it is, they actually do commute. So we can kind of dispense with this silly thing and just have 2 here, like the way we normally do. But before you do that, whenever you're dealing with the operators, you kind of want to make sure that they do commute before you do that. So now what we need to deal with is, I think what we have here is already enough to show that the state I have here is not an eigenstate. So this is going to be a kind of a hybrid thing. So let me organize my work this way. And if anything's not clear, raise your hand and let me know. So I'm going to do a version of this, except I'm not going to do 4x4 matrix. Because apparently when you do that, then you are messing up something so it doesn't work. So this is what I want to calculate and see if it's true. If I have this state, psi spin up 1, product space width, psi spin down 2, is it true that if I act on this with j squared operator, do I get 0? Let's try out the calculation and see. So what this is, let me just write out the portion so that I minimize the amount of calculation I have to do. So this is, let me call this operator Q. So I'm going to deal with this on its own separately. So what this is, it's S1 squared plus S2 squared plus 2Q acting on this state. Psi spin up 1, psi spin down 2. And these two operators are kind of simple to deal with because it's dealing with only one of the two particles, doesn't affect the other. So I can kind of get the result with these first two. These first two, they're just going to give me, they're going to lead to, well, 3h bar squared over 4 plus 3h bar squared over 4 acting on the state, right? That's what I handle with. So what I have to handle is this Q. Let me do one sample calculation. I think that's better. So Q is a sum of 3 terms. So let me just do this. Let me do this one as a sample calculation. I think that's going to be a lot better. So this is what it's going to look like. That operator acting on this, S1x, as 2x acting on this state. It looks a lot cleaner if I attach the operator to the states they are actually able to act on. So I'm going to write it out this way. S1 acting on this, acting on psi spin up 1, product space with this operator acting on this, S2x psi spin down 2. Good? All right. And the rest I carry out the calculation with the matrices, because this spin-up state is not an eigenstate of this. So when you write it out, it looks complicated. It's easier to do it in the matrix form. So imagine multiplying with this on the spin-up state. Then you end up with, I guess, just h bar over 2, 0, 1, right? So this times that is 0. This times that is 1. So for this first state here, you end up with this h bar over 2, 0, 1, product space. So this is for particle 1. I had to keep the label so that I remember what particle it goes with. For this one, it will be spin down state with this. Oh, it's 1, 0. So it's, hey, did it just flip around? H bar over 2, 1, 0. Okay. So, all right. So my state has changed. So this state is definitely not the same as, so I guess if I collect it back out, what this is, this is, this scalar moves through, so I have h bar squared over 4 multiplied to this state. Spin down 1, so spin down 1, and spin up 2. Spin up 2. And this state is not the same state as this, which means it's not an eigenstate. And so actually, let's just all write it out. So we've already started here with these two. Let's just kind of just keep writing out what this 2q is. We just did it here. So it's a plus 2 times, we worked this out. So it's h bar squared over 4. Not even the same state. Psi down 1, psi up 2. And if we do it for y and z, at least I think with z we are going to get the same state, right? Let's just use this space to do all the calculation that requires matrices. So when we are dealing with now the y component, it's S1 y, same state, y, y. So all right, let's imagine acting with this on this. So I get, let me do this carefully. I made keep making the same mistake. This multiplying to this. So this times this is 0 for the first row. This multiplying to this is I for the second row. So it's supposed to be 0, I. And for the second particle, let's do this carefully. This multiplying to this gives me minus I for the first row. And this multiplying to this gives me 0 for the second row. So minus I, 0. Yep. So, all right. How do I put it? I should factor out an I. So when I write it out, let's see what it is. I imagine factoring out I here. So this is 1 times I. I factor out minus I here. So this is 1 times minus I. Good. Now I can simply multiply these two. I times minus I get 1. So, so it's just h bar over 2. Spin down, spin up. Good. Oh, so I get another one of this. So I get 2 of these. Let me, since this is a very unfamiliar calculation, let's just do it for g to make sure that we are not making any unexpected mistakes. So this is, by the way, the thing to become kind of watch out for in quantum mechanics, that the calculations you are doing are very different from other calculations you do. So it becomes even more important that you know the rules and you're applying the rules very carefully. So S1G, G applying to that, G, G applying to that. So I get h bar over 2 for spin up, and I still end up with the same spin up, right? G doesn't change anything. So here it's spin down. So instead of h bar over 2, it should be minus h bar over 2. All right. So, and it should remain spin down. So 0, 1. Let me get rid of these i's. All right. So now you end up with spin down and not spin down. You skip spin up and spin down as it was before, right? And instead of h, you have minus h bar squared over 4. Okay, so that's a difference. So let me write that out. Minus h bar squared over 4 psi, and this is a distinct state from that other state. Otherwise, we could have tried to combine them, but these two states are different. Right? So I have that. Do they look like they will add to 0? I mean, okay, so this can cancel some of this, right? So I have factor 6 quarters. They can go down to 4 quarters. But after that, we are kind of done. We kind of wish somehow this came out in a way that cancels this, but it doesn't. So this is a very long-winded way of covering. This is why I need to have worked this through. That this is not an eigenstate of this operator. When we just try to combine spin up and spin down into a single product state like this, then it doesn't give you a total angular momentum eigenstate. It gives you, when you try to measure the total angular momentum, you don't even get the same state back, because the state that you get back is a combination of this, which is what you started out with, mixed in with some of this, which is not what you started out with. So, so that's the challenge here. How do you combine two spin states in such a way that it is an actual eigenstate of this operator? And if you've been following this carefully, there's a kind of a hopeful solution that you have seen actually on Tuesday. Do you guys remember exchange symmetry on Tuesday? Exchange symmetry, I guess we covered it towards the end. Multi-particle state, where you, in the wave mechanics, you describe the total multi-particle state with the product of particle state 1, particle state 2, and how these are indistinguishable particles. So when you swap the particle positions, you should have same function, but you don't. And what was the solution to that? How do you build a state that is exchange symmetric? Like, so if you have, yeah. So if you have psi 1, let's say x1, and psi 2, x2, the way we built a symmetric state was by, okay, so you have the product, and let's add it to another product with these two swapped, pre-swapped. So the even state that we built, even, it looked like this: psi 1, x1, psi 2, x2, multiplied, just regular algebra multiplication, plus psi 1, x2 times psi 2, x1. So that with the particle exchange operation, when you swap these two, then this swapped becomes, well, that. And this swapped becomes this. So you get the same state back. The reason I'm bringing it up here is because of what this reminds me. All that this state is, it's this state, except you swapped which particle is spin up and which particle is spin down. So maybe we pre-counter that. So instead of building our state like this, maybe we build it this way. We build it so that we are dealing with this. So I spin up 1, so I spin down 2, and as we are acting with this operator, we think those two particle states are going to be swapped. So let's add the swapped version, pre-add to it. So I spin down 1, so I spin up 2. So this is our proposed total wave function state. Then, so let me, so I've been talking nonstop for a while. Let me give you this to exercise. Try working out this calculation and see what you get. You will get an eigenvalue, or you will be able to find that this is an eigenvector, but the eigenvalue will be a little bit different from what you might be expecting. Because I know there's a mistake here. So let me leave you to that calculation. So let me write out. So let me clean this up here, and then let me write up the question that you are supposed to be answering. So this operator, when you expand it all out, it's s1 squared plus s2 squared plus 2 sx1 sx2 plus sy1 sy2 plus sg1 sg2. Okay, so that's the operator. And this is the question I'm asking you to answer. And I think you have seen enough now to actually do this calculation. Or if you have any questions, you can call me and I'll come by and help you with it. So the question is, what is the eigenvalue of psi of 1, or let me call that psi. This is my psi, of psi with operator j squared. Yep. So it'll take some time because there's a lot of math to go through. So let me give you however much time, 10, 15 minutes. I'll be walking around, answer questions, and yeah. And I happen to know the correct answer without doing the calculation, so I can check your answer when you find it. So the question is, what is the eigenvalue of psi with operator j squared? Yep. So it'll take some time because there's a lot of math to go through. So let me give you however much time, 10, 15 minutes. I'll be walking around, answer questions, and yeah. Let me highlight the key step. This is the key step that involves math that you are not familiar with. This is the key step. That when you are acting with an operator that involves both particles, you want to group the operator with the correct particle. Group the operator with the correct particle. Once you have done that, so that this is all space 1, this is all space 2, then you can get through the rest of the calculations. I used to have a professor who said his hand can do the algebra much better than his head can. And what he meant was that if you are staring at it and trying to do it in your head, you won't be able to do it. This is too complicated. But when you work through it component by component, things will eventually simplify. So if you're staring, I would recommend that you start out with something like this, expand this out to this, which is this, acting on these two. So actually, you've seen me do it for one of them already. So you're really doing it for the second portion. So you have this result for the first portion already. Add it to the result of the second portion. And then collect like terms. These are your two terms. Collect like terms, simplify the coefficients, and you will kind of see something emerging out of that when you write it all out. So I guess for those people who are staring at the board, that's what I'm telling you is stop staring and start writing, because it'll get done a lot more quickly that way. Maybe either make your work easier or verify something you already know. So call this expression A, and let me write down the simplified version of A here. Let me pass out something called the Clebsch-Gordan coefficient. That's what we're going to wrap up today with. Once you're done with the calculation and we answer our next question, I have something to show to you that's on this table. But I will, point out what you're supposed to be doing with it when we get to that point. Okay, good. Okay, that's long enough. So let me write down so what I was telling you is you already have of these two terms. You already have the one that corresponds to this. You only need the one for this. So this could be the calculation you are doing. And if you did that, for the second part, this is what you should have ended up with. H bar, I guess if you're keeping it in the same order, then it would be psi down 1, psi up 2, plus H bar squared, psi up 1, psi down 2. But these are kind of these to match. So that's how you end up with the eigenstate. And when you add them, so right, add them together. So after adding them through, what you should end up with is 2 H bar squared and the original state that you started out with. So your final answer is surprisingly simple. It's a 2h bar squared. That's your eigenvalue. Now the step getting to that, it's a long calculation. I don't want to minimize that. It is a long calculation. And I won't say this is true of every calculation, but this is something you would see like component by component proof, or there are some types of calculations where it's not so complicated as long as each individual step you know how to do. If you have the final result, you know how to simplify. It doesn't take any sophisticated techniques. Just have to chalk through it. That's really the only advice I have. Have enough time, just chalk through the calculation. I will never give you on an exam something that looks like that. But that's an ideal homework question where you just do an hour of algebra and you get a very simple result to which you can assign a meaning. So it's h bar squared times 2. This is supposed to be my L angular momentum squared. Let's refer back here. So L squared, h bar squared times L plus 1. If my value of L was 1, then that would match with this 2, right? So the state that I got, this state here, this is consistent with, I guess, let me make up a quantum number value of 1, not 0. So you added the two, one spin up, one spin down, and you ended up with a total spin of 1. Now, what this state is, it has a projection of 0 along the z-axis. So it's a spin 1 that points in some orthogonal direction that's not z-axis. So what would you change it for those of you who finished the calculation? And this is where you would actually gain some insight from having done the calculation. What would you change so that you end up with, instead of j equals 1, you actually end up with j equals 0? What change would you make to this state so that you get total angular momentum equal to 0? Yeah, instead of plus, it's a very simple change. You would change this to minus to get total angular momentum of 0. Yeah. So this is the simplest possible, non-trivial angular momentum addition calculation. And what I passed out while you're doing that calculation is called the Clebsch-Gordan table. While you stare at that for a little while, let me bring the projector back so that I can show you how to read the Clebsch-Gordan table. So you could have actually read your result off of the Clebsch-Gordan table instead of actually doing the calculation. So what this is this long calculation you just went through. It is a long calculation. If you had to do it every time you needed the result, it would take you forever to do anything useful. So somebody has done this calculation all for you already. Let me just bring up the table. So the table actually has way more than you need. Let me zoom into the portion that I want. So I'm looking at the smallest table there, 1/2 by 1/2. That's indicating you are adding spin 1/2 system to another spin 1/2 system. Good. And it's telling you, so what's down horizontally is different ways of combining them. And what's on the along the column is the end result, the total angular momentum value. So let me give you one. So let me give you some labels so that you know what the numbers stand for. So these numbers here, these stand for the quantum number j, stands for this total angular magnitude of total angular momentum. Good. And these numbers here stand for the projection of that angular momentum along z-axis or a chosen axis. It's usually z-axis. Good. So let's deal with the simple ones first. If you want total angular momentum 1 pointing along, z-axis, then you would add the two particles as a spin up, right? So that's what this is showing. This is the coefficient for spin up, and you are really multiplying them together, the direct product that we have been talking about. And it comes with a coefficient 1. And if you want you to get this, then it's a spin down, just the same thing. So it's this thing, direct product with this thing, that gives you -1. Now to get the projection of 0, you can end up with two different ways to get projection of 0. You can have 0 total angular momentum, then projection will just like 0 is the only option left. Or you can have a total angular momentum of 1, but just oriented in a different direction so that your projection is 0. So in order to get this is how, wow, these are really running into each other. So, okay, let me add the notation so that you can kind of read it. So this is the wave, the vector state. This is the spin state that is represented here. So this would be, let me call this A, call this B. So this would be A, and this would be B. Good? And what here is telling you is add these two states with a minus sign in front of them to end up with a total angular momentum 0. add the states with the same sign to end up with a total angular momentum 1. And the thing about the coefficients, so when they say 1/2, they really mean one, square rooted. Square rooted, so that it ends up being a normalized state. So with the spin 1/2 system, like you knew nothing coming into this, and you were able to do this calculation, figure out the state you were given was either this or this. So spin 1/2, as I said, simplest non-trivial system. You can do it coming into like this period knowing nothing about this. Now, as you start to add more, if you're adding spin 1 to spin 1/2, you're adding spin 2/3, 3/2 to spin 1, then it gets a lot more complicated. That's what the rest of the table is for. Like what I have there is this very small portion of this table. The rest of the table is for more complicated addition of angular momentum. And so once again, I think I started the day with this. Whatever we cover today, we are not being tested on. This is supposed to be fun exercise, something that's beyond what we are supposed to cover in Physics 4C. You don't need to know any of this for the exams. I'm not going to touch on it. But I just want you to give you a glimpse of if you are taking upper division. I don't think it actually covered this in upper division quantum. If you're able to go more into quantum mechanics, what some of the quantum mechanical calculations involve. And I would just tell you that angular momentum is one of the most quintessentially quantum mechanical thing, because there's really nothing that's classically anything like a quantum mechanical angular momentum. That's why there's a whole table built just to accommodate that. And this becomes a model for other symmetries of nature, something called the isospin that comes up in particle physics. The symmetry is modeled after symmetry of angular momentum, but isospin has nothing to do with the spin. There's a color, anyways. This does go into more abstract math than we are supposed to in this class.